Alright, so this is LeetCode 100. It's called same tree. So given the roots of two binary trees, P and Q, write a function to check if they are the same or not. Two binary trees are considered the same if they're structurally identical and the nodes have the same value. So let's look at an example. So given these two binary trees, this would be the root node P and this would be root node Q. We're going to check if they're identical or if they're the same tree. Sorry about that. So we're going to check if they're identical. So structurally, they look the same, right? They have a root node and a left child and a right child. And then in terms of the values, they match as well. So the root node is 1 right here. Both of these match, right? Then both of the left children match the same value, then both of the right children match. Okay, so that's why we would return true for this input. Let's go ahead and erase this. For this input, we would return false because although they have the same matching values, this is the left child and then this is the right child. So they're not structurally the same, so we would return false. The next one we would return false because while they are structurally the same, the values aren't the same. So 1 and 1 match, 2 and 1 do not match. These left children do not match. So you can see that the nodes that are in the same position should match the values, and in this case they don't. So we would return false. P and Q are going to initially start at this root node, right? And then we're going to, in the second iteration here in purple, P and Q are going to be on the left children, so this 2 in the Q. Then on the third iteration, we're going to have P and Q be equal to these nodes, the right children. Well, how are we going to stop this recursion, and like what's going to be our base case? Well, if we looked at the back on LeetCode, you can see the list node class, but you can see that if we don't have a left and a right subchild, then it's automatically going to be none or null. Right? So all of these nodes, and then these nodes are going to have none as well. So it's going to, I don't feel like copying and pasting them, but what I'm trying to get at is the base case is going to be that the left and the right subchild are equal to none, right? So there are no values there. There's no nodes, but they still have the same structure because the left and the right, it's almost like it's symmetric, right? So this left child, even though this node doesn't visually look like it has any children, it actually points to none. So green is the first iteration, right? Purple is a second, pink is a third. What about on our fourth iteration, right? So this P is going to go to here. And then this Q is going to go where? It's going to go to here. So we're just continuously doing the pattern that we were doing above. And so we're going to check, does this none equal this none? It does. So then we're fine. And that's going to be our base case because we know that there's going to be no more subchildren. These none don't point. This isn't an actual node. This is just a default value, right? And then we're going to continuously do that. So with the other nodes, right? So we're going to then go to this node over here, and this would be the next iteration. I hope that explains the recursion a little bit more. Yeah, I'm going to go ahead and get into the actual code. Okay, so with recursion problems, you want to state your base cases, and like I was saying on the whiteboard, our base cases are going to be when the children are equal to none. So when P and Q are equal to none, in other words, I can just say it like this: when if P is equal to none and Q is equal to none, then return true, right? Otherwise, what's going to be our next case? Well, our next case would be kind of, I believe, the recursive case. So we could say, we could do elif. Actually, we can do elif or if, but I'm just going to do if. If, what are the things we want to keep track of, right? We want to keep track of if they're structurally identical, right? What it says here, if they're structurally identical and the nodes have the same value. So structurally identical, how could we make that? How could we make that check here? Well, we can just say if P does not equal none and Q does not equal none. So if both of these values at this point are they're a node, they're an actual node, right? They're not equal to none. Then we want to make sure that they have the same value, right? So we can say and P dot value is equal to Q dot value, or just val actually. Then inside of here, what we want to do is we want to do the recursive call, right? So we want to do we're going to store a value. So left children, and we're going to do a recursive call. So we're just going to do left children is equal to self dot is same tree with P dot left and Q dot left, right? So we're going to give it, if we remove all this kind of thing so we can see what I'm talking about. So initially this if statement is going to check these values, right? So they're not equal to none, but it's going to check this if statement on line 12. It's going to say, is P equal to none? No, it's not, because P is going to be equal right here. It's going to be set to this value. Is Q equal to none? No, so that means that they're structurally the same so far. Then we're going to say, are the values the same? They are. Okay, so then we go in here and we're going to do the recursive call. And what we're going to do is right, in the second iteration, we want to give it the left children of P and Q. So we're going to say self dot is same tree P dot left, which is this node, and then Q dot left, which is this node, because then we want to do the same check for this node. Okay, and then we're just going to do the same thing, but we're going to do it with the right children. So we're going to do right children is equal to self dot is same tree. I'm going to do P dot right and Q dot right. Okay, and then what are these going to actually be set to? These are both going to be set to a true or false value, right? Or false, because these are the function calls. This is the recursive function call, and this is going to either return true, or actually we haven't even returned false. So our last case, or kind of like our case where none of these or these conditions aren't met, then we're just going to return false, right? False, got that wrong. Okay, so this is going to be these values, left children and right children, are going to be set to a true or false value, and we only want to return true in the entire function in the same tree when left children and right children are true. So if left children and right children I'm just going to explicitly say is equal to true and write children is equal to true. Then we can just return true. Yeah, I think that's the algorithm. Let's see if I made any mistakes. Yeah, so that's the algorithm. It's can get a little confusing with the whole recursion thing, but I think the more that you get exposed to it, it's going to become more natural. So what's the time and space complexity? Let's see. So the time complexity, time would be big O of, well, big O is the worst case scenario, right? So the worst case scenario would be that we would have to iterate through every node in both trees. So we would have to iterate through this node, this node, this node, this node, this node. So let's say that the length of this tree right here, and that I'm putting the arrow in blue, let's say that's of size P, and then let's say the length of this node, or this tree, the number of nodes in this tree is of size Q, so it's going to be, the time is going to be big O of P plus Q, right? Because in the worst case scenario, we need to visit every node in both trees. Okay, and the space complexity, that is a little tricky. Initially, it seems like we're not using very much space, right? We are using some variables, but these variables aren't going to scale as our input size grows. But because we are using recursion, I think that we're unintentionally using space. We're going to be using something called the call stack. So the call stack keeps track of, I believe, the function calls in recursion. You might have to fact check me on this, but I'm pretty sure recursion uses the call stack. And so I think that the call stack would go to the height of the tree. So if whatever the greatest height is of the tree, so we would do maybe, I say that the height of P, of this P tree right here was, I'm going to do it in red. Say this height was, it looks like it's 2, right? And then this height over here is equal to 2. So, and let's just label them variables so that the call stack would go to, at most, I believe, of size 2. I might be wrong with that, but that's what I believe it is. And then let's just say that the height of this tree P was P H, and then plus, actually it might not be good to use 2 variables, 2 letters for a variable. What else could we use? We can use just use H, and we can use X and Y actually. I'm trying to think of variables we haven't used. So let's say that the height of the left tree is X, and the height of the right tree is Y. Then I believe that would be the time complexity, I think, or the space complexity. I think that the stack can grow to of this size, where basically we our stack can grow to the size of X plus Y, where they're both the height, so of size possibly 4, I believe, in this case. Space always kind of gets me with recursion problems, so I might be wrong with this, but I'm pretty sure this is the time complexity. But yeah, comment down below if you think otherwise. Cool, thank you.